Hello, in this lecture we find out the size of angle X. In the drawing we have a quarter circle, AOB is a quarter circle. We know that angle AOB equals to 90 degrees because of the fact that AOB is a quarter circle. In addition, inside the quarter circle we have line segment AP that equals to line segment PQ. This is angle APQ, that is a right angle. And our task is to find out the size of this angle, angle PQB, that is equal to X units in its size. We have to find out the value of angle X. So in the first step, we complete the quarter circle to a semicircle. So we completed the quarter circle to a semicircle. We find this point as point M. So ABM is a quarter circle, and therefore AM is the diameter of the quarter circle according to our construction. So as you know, AM is the diameter of the semicircle according to our construction, because we completed the quarter circle to a semicircle. So we can write here that AM is the diameter of the semicircle according to our construction. AM is the diameter, it is absolutely straight line, so if we focus on the left side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the left side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will extend the straight line PQ by straight line until it touches the semicircle. But the real question is where the extended straight line PQ will touch the circle after we extend it. So we will assume that the extended side PQ will touch the circle and to this point, point N. Okay, according to our assumption, the extended side PQ will touch the semicircle at point N. So, therefore, we will have here peripheral angle APL. Peripheral angle APL is equal to 90 degrees in its size according to what is given in the question, and peripheral angle APL subtend on AL. peripheral APL subtend on AL. But AL, it is definitely not the diameter of the semicircle, because the center of the semicircle is at point O. And because of the fact that chord AL doesn't pass through the center of the semicircle, it cannot be the diameter of the semicircle. Now we have contradiction to rule 5. So a bit quicker on rule 5. Any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So in the rule we have a circle. This is peripheral angle AOB that is equal to 90 degrees in its size. And therefore, according to this rule 5, peripheral angle AOB must subtend on AEB, that is the diameter of the circle. But here we have contradiction to rule 5. One, because we have here peripheral angle APL that is equal to 90 degrees in its size according to what is given as the question, but still it does not subtend on the diameter of the circle. It subtends on AL, and AL definitely is not the diameter of the semicircle, because it doesn't pass from point O, that is the center of the semicircle. And we know that any diameter of a circle or a semicircle must pass through the center of the circle. And because of the fact that APL subtends on AL, and AL is not the diameter of the semicircle, we have contradiction to rule 5, because peripheral angle APL that is equal to 90 degrees inside must subtend on the diameter of the semicircle, but it subtends on AL that is not the diameter of the semicircle. Likewise, we will assume that the extended side PQ will touch the circle here, its point edge. You can actually complete the semicircle to a circle. So we'll assume that the extended side PQ will touch the circle here at point edge. Okay? So peripheral angle APL that is equal to 90 degrees in its size subtend on a edge. It subtends on a edge because, according to our assumption, the extended side PQ will touch the circle at point edge, and therefore peripheral angle APH subtend on a edge. Still, we have the same contradiction to rule 5, because we have peripheral angle AP edge that is equal to 90 degrees in its size. Therefore, peripheral angle AP edge according to rule 5 must subtend on the diameter of the circle or semicircle. But here it subtends on a edge, and a edge is definitely not the diameter of the semicircle, because it doesn't pass through point O, that is the center of the semicircle. So due to those two contradictions, we must arrive to the conclusion that the extended side PQ will touch the circle at point M, and only at point M, and not in any other point. Well, because if you touch the circle at any other point, then peripheral angle APM, peripheral angle APQ, or peripheral angle APL or peripheral angle APH will not subtend on the diameter of the circle, because AH is not the diameter of the circle, and AL is not the diameter of the semicircle, and AH is not the diameter of the semicircle. So due to those two contradictions, we must conclude the extended side PQ will touch the semicircle at point M, and only at point M, and not in any other point. So the extended side PQ start the circle at point M. Now we don't have any contradiction to rule 5. Why? Because we have peripheral angle APL that is equal to 90 degrees in size, and indeed it's a subset on AM that is the diameter of the semicircle. AM is the diameter of the semicircle according to our construction. Why? Because we completed the quarter circle to a semicircle, and therefore AM is the diameter of the semicircle according to our construction. So we have peripheral angle APM that subset on AM that is the diameter of the semicircle. We don't have contradiction to rule 5 anymore. It's exactly according to rule 5 because we have peripheral angle APL that is the right angle. So peripheral angle APM subset on AM that is the diameter of the semicircle exactly according to rule 5. In the next step, we join points A and Q together by a straight line. By joining points A and Q, we created the right triangle that is also an associated triangle, triangle APQ. Why triangle APQ is the right triangle? Because this angle is the right angle. Triangle APQ is also associated triangle because side AP equals to side PQ according to what is given in the question. So, what are the sides of those two angles? We have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other in their sizes. We know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, therefore it is also true in the right associated triangle, triangle APQ. So which angles we have in the right and associated triangle, triangle APQ? We have this angle that is a right angle, that is to say it is equal to 90 degrees in size, alpha plus alpha, that is 2 alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees. It is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So okay, this is angle alpha that is equal to 45 degrees in its size. And this is also angle alpha that is equal to 45 degrees in its size. In the next step, we will prove that the right triangle AQO, this right triangle, is similar to this right triangle, triangle OQM, according to side angle side congruency rule. So why those two right triangles are similar to each other? First of all, point O is the center of the semicircle. Point A is the point of the semicircle itself, therefore always the radius of this semicircle, we define the radius of this semicircle is equal to R. Likewise, point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of this semicircle is equal to R according to our definition. So we can write down that we have to prove that the right triangle AQO congruent to the right triangle OQM. So first of all, we found out that AO equals to OM equals to R. They are both the radii of the circle, therefore they are equal to each other. So I'll write it down. AO equals to OM equals to R. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So angle AOQ in the right triangle AOQ is equal to this angle, this is angle MOQ, they are both equal to 90 degrees in their sizes, therefore they are equal to each other. And finally, OQ is a common side that belongs to both triangles, so can I know that OQ equals to itself is a common side that belongs to both triangles. OQ equals to itself is a common side that belongs to both triangles. So if you prove that those two triangles are similar to each other according to side angle side rule. So write it down. Triangle, the right triangle AQO congruent, this is the side of congruent, to the right triangle OQM according to side angle side rule. That is to say that we found out that those two sides and the angle that is included between those two sides in triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right triangle OQM. Therefore, those two right triangles are similar to each other according to side angle side rule. And for the fact that those two triangles can go into each other, we will derive that side AQ or the right triangle AQO is equal to side QM in itself. AQ equals to QM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So AQ equals to QM. AQ equals to QM. So in the right triangle, in the big triangle AMQ, we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in triangle A, the big triangle AQM, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So here I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. This is triangle ABC, that could be any triangle. Those three angles alpha, beta, and gamma are defined as and triangles because of the fact that they are located inside the triangle, while this angle is defined as an triangle because it is located outside triangle ABC. According to this rule 8, the size of this angle E, that is the triangle of triangle ABC, is equal to the sum of the two triangles that are not adjacent to it. We have three triangles in triangle ABC, alpha, beta, and gamma. Angle gamma is adjacent to angle E, but the size of angle E equals to the sum of the two triangles that are not adjacent to it. So alpha and beta are the two triangles that are not adjacent to angle E. Therefore, in total, we found out that the size of the angle E is equal to alpha plus beta, according to this rule 8. So the size of the external angle E is equal to the sum of the two triangles that are not adjacent to it. That is to say, angle E equals to in its size to alpha plus beta. So can actually implement rule 8 in our drawing. Why? Because in our drawing, if we focus on the big triangle AQM, this angle equals to 45 degrees in its size, and in relation to the big triangle AQM, angle AQP is defined as an external angle of triangle AQM because it is located outside triangle AMQ. Those two angles are defined as triangles that are not adjacent to this angle. This angle is adjacent to this angle. The two other triangles that are not adjacent to it are those two angles, that each of them is equal to beta. So according to rule 8, again that the size of this angle AQP equals to the sum of the two triangles that are not adjacent to it. That is to say, angle AQP equals to beta plus beta. So write it down. We found out that according to rule 8, the size of the triangle AQP is equal to the sum of the two triangles that are not adjacent to it. In relation to the triangle AQM, those triangles are defined as the triangles that are not adjacent to this angle. So beta plus beta equals to the size of the external angle AQP. The size of external angle AQP, according to rule 8, equals to beta plus beta, that is 2 beta. So angle AQP equals to 2 beta, but we have already found out that the size of angle AQP is equal to 45 degrees. So we can substitute the external angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divide this equation by 2 and find again that the size of angle beta is 45 degrees over 2. 45 degrees over 2 is 22.5 degrees. This angle equals to 22.5 degrees in its size. This angle also equals to 22.5 units, 5 degrees in its size. Those two angles are both equal to 22.5 degrees in their sizes. So in the next step, we will focus on the right triangle QOM. We know that the sum of the angles in the right triangle OQM must be equal to 180 degrees. So which angles we have in the right triangle OQM? Angle beta equals to 22.5 degrees in its size, plus this angle that is the right angle, that is to say it is equals to 90 degrees in its size, plus this missing angle. In total they must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So the missing angle is the angle OQM. Okay, again, the sum of the angles in this right triangle OQM must be equal to 180 degrees. Again, the sum of the angles in this right triangle OQM must be equal to 180 degrees. That is to say, angle beta that is 22.5 plus the right angle that is equal to 90 degrees in its size, plus the missing angle OQM, in total they must be equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 22.5 degrees plus angle OQM is equal to 180 degrees minus 90 degrees, it is 90 degrees. So 22.5 degrees plus the missing angle OQM must be equal to 90 degrees. So here we subtract 22.5 degrees from this equation, and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is equal to 67.5 degrees. So if you found out that the missing angle in this triangle OQM is equal to 67.5 degrees in its size. So here those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. That is to say, angle X equals to 67.5 degrees in its size. Angle X is equal to 67.5 degrees in its size, according to the rule that states that vertex angles are equal to each other. So the answer to the question is the size of angle X is 67.5 degrees in its size. So we finished with this question. So in the next step I will summarize the lecture. In this lecture, our task is to find out the size of this angle, angle X. So in the drawing we have a quarter circle, AOB is a quarter circle, and we know that angle AOB is a right angle because of the fact that AOB is a quarter circle. It is given us the question that AP equals to PQ, and we know that this is angle QPA or APQ is equal to 90 degrees in its size, according to what is given as a question. This angle equals to 90 degrees because AOB is a quarter circle. Again, our task was to find out the size of this missing angle, angle PQB is equal to X degrees in its size. We have to find out the value of X. Okay, so first of all, we completed the quarter circle to a semicircle. We define this point as M. So, according to our construction, AM is the diameter of the semicircle. Again, we created here a semicircle, and according to our construction, AM is the diameter of the semicircle. Here, AM is the diameter of the semicircle, and now we joined point, we extended the straight line PQ by a straight line, but the question is where the extended side PQ will touch the semicircle. We assume that the extended side PQ will touch the semicircle at this point, point L. But if the extended side PQ touches the semicircle at this point, point L, then we will have contradiction to rule 5, because we have peripheral angle APL that is equal to 90 degrees in size. So peripheral angle APL must subset on the diameter of the semicircle, and AL is definitely not the diameter of the semicircle, because we know that AL doesn't pass from point O, that is the diameter of the semicircle, and we know that any diameter must pass from the center of the semicircle. And because of the fact that AL doesn't pass through the center of the circle, it is contradiction to rule 5, because we have peripheral angle APL that is the right angle, and it must subtend on the diameter of the semicircle, but AN is not the diameter of the semicircle. We also assume that the extended side PQ will touch the circle at this point, point H. So we have the same contradiction to rule 5, because we have peripheral angle APH that is equal to 90 degrees in its size according to what is given us the question, and it's absent on AH. AH is definitely not the diameter of the semicircle, because it doesn't pass from point O. So due to those contradictions, we must conclude that the extended side PQ will touch the semicircle at point M and not in any other point. Now we don't have contradiction to rule 5 anymore, because we have peripheral angle APM is equal to 90 degrees in its size, and indeed peripheral angle APM subtend on AM, that is the diameter of the semicircle according to our construction. Again, AM is the diameter of the semicircle according to our construction. Okay. In the next step, so AM is the diameter of the semicircle, it is absolutely a straight line. So if you focus on the left side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line must be equal to 180 degrees. So which angles we have at the left side of AB at point O? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees. And therefore, this missing angle must be equal to 90 degrees in its size according to rule 3. In the next step, we join points A and Q together by straight line. By joining points A and Q, we get the right triangle that is also an associated triangle, because triangle APQ is the right triangle because this angle equals to 90 degrees according to what is given us in the question, and it is also an associated triangle because AP equals to PQ. So in the right associated triangle, the sum of the angles must be equal to 180 degrees. So which angles we have in the right and associated triangle, triangle APQ? We have this angle that is 90 degrees, and in front of those two equal sides, we have those two angles that must also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So those two angles are both equal to alpha. So which angles we have in the right triangle PQ? We have this angle that is a right angle, it is equal, that is to say, it is equal to 90 degrees in size. Alpha plus alpha is 2 alpha. So 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. 2 alpha equals to 90 degrees. So here we divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2 is 45 degrees. This is angle alpha that is equal to 45 degrees in its size, and this is also angle alpha that is equal to 45 degrees in its size. Okay, in the next step, we prove that right triangle AQO congruent to the right triangle OQM according to side angle side rule. So why those two right triangles are congruent to each other? First of all, AO equals to OM. They are both the radii of the semicircle, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, OQ is a common side that belongs to both triangles. So we can write down that OQ equals to itself is a common side that belongs to both triangles. So if you prove that those two sides and the angle that is included between those two sides in triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in triangle OPM. And therefore those two right triangles are similar to each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in triangle AOP are correspondingly equal to those two sides and the angle that is included between those two sides in triangle OQM. And therefore those two right triangles are similar to each other according to angle and similarity rule. And again, if you know that the right triangle AQO congruent, this is the sign of congruent, to the right triangle OQM according to side angle side rule. And from the fact that those two right triangles congruent to each other, we write the side AQ of the right triangle AQO is equal to side QM of the right triangle OQM in its length. Because again, we derive that AQ equals to QM. In the next step I presented to you, but before that, AQ equals to QM. According to the rule that corresponding sides in congruent triangles are equal to each other. So those two triangles congruent to each other, therefore the two corresponding sides, that is to say, AQ and QM must be also equal to each other. So in the big triangle AQM, in front of those two equal sides, we have those two angles that also must be equal to each other in their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta. Okay? So in the next step I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 8. Rule 8 relates to the size of an exterior angle. So in the drawing we have triangle ABC that could be any triangle. Alpha, beta and gamma, all of those three angles, they are defined as the interior angles because they are located inside triangle ABC. While this is angle A, angle ACF equals to E degrees in its size, it is defined as an exterior angle. While angle E is an exterior angle because it is located outside triangle ABC. So what is the size of the exterior angle E, or what is the size of angle ACF that equals to angle to E according to our definition? The size of angle E equals to the sum of the two interior angles that are not adjacent to it. Those are the two interior angles that are not adjacent to angle E. Angle gamma is an interior angle that is adjacent to angle E. So the sum of the two interior angles that are not adjacent to angle E are alpha plus beta. Alpha and beta. So alpha plus beta equals to angle E. And again, the size of angle E according to this rule 8 equals to alpha plus beta, that is the size of the two interior angles that are not adjacent to angle E. E equals to alpha plus beta. So we can actually implement a new rule in our drawing. Well, because in our drawing, if we relate to the big triangle AQM, this is actually if we relate to triangle AQM, actually we relate to triangle OQM, to this right triangle OQM. So in the right triangle OQM, No, we relate to the big triangle AQM. In the big triangle AQM, this is the external angle AQP. The size of the external angle AQP must be equal to the sum of the two triangles that are not adjacent to it. This angle is adjacent to this angle. The two other triangles in the right triangle AQP, the two other triangles that are not adjacent to this angle AQP are beta and beta. So the size of the external angle AQP must be equal to beta plus beta equal to 8. So if you look to the big triangle AQM, triangle AQM, the size of the external angle AQP, the size of this external angle AQP equals to the sum of the two triangles that are not adjacent to it. That is to say, it is beta plus beta. According to rule 8, if you relate to the big triangle AQM, the size of the external angle AQP equals to beta plus beta, that is 2 beta. But we have already found out that the size of the external angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees, and substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divided this equation by 2 and finally found out that angle beta equals to 45 degrees over 2 is 22.5 degrees. So this is the missing angle beta. This is equal to 22.5 degrees in size. This is also the missing angle beta. This is equal to 22.5 degrees in size. Okay, so if you focus on the right side OQM, in this triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is 22.5 degrees. This is the right angle plus this missing angle, that is actually angle OQM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in this right triangle OQM, the sum of the angles must be equal to 180 degrees. That is to say 22.5 degrees plus 90 degrees plus the size of the missing angle OQM. This is the missing angle OQM. In total, the sum of those three angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation and finally found out that 22.5 degrees plus OQM, the missing angle OQM, must be equal to 180 degrees minus 90 degrees. This is 90 degrees. So 22.5 degrees plus the missing angle OQM in total must be equal to 90 degrees. Here we subtracted 22.5 degrees from this equation and finally found out that the missing angle, the size of the missing angle OQM equals to 90 degrees minus 22.5 degrees is 67.5 degrees. So the size of the missing angle OQM is 67.5 degrees in its size. This is the missing angle OQM that is equals to 67.5 degrees in its size. So those two angles are defined as vertex angles, and we note that vertex angles are equal to each other. Therefore, the vertex angle X is equal to the vertex angle that is 67.5 degrees. So in total, we found out that the size of this missing angle X is equal to 67.5 degrees in its size. And again, we found out that the size of the angle that we are looking for in this question, that is angle X, is equal to 67.5 degrees in its size. And that is the answer to the question. Okay, thank you very much.